Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to take a look at section 5.3 in our textbook, and this is called Cramer's Rule. So the first video here, 5.3, we're going to find out the idea behind Cramer's Rule. Now, Cramer's Rule is a method to solve ax equals b. Now here's the twist. Ax equals b using the determinants. Now, the obvious problem with this is that you can only take a determinant of a square matrix. And so the problem is ax, so that's just a vector, and b, that's just a vector. These are not square. They are not square matrices. So the idea then is, how do we make those square matrices? Well, we're going to assume A is square. Assume A is square. And we're going to let A equal, now for this example, we're going to use a 3 by 3 matrix. I think a 2 by 2 is not quite enough to see what's happening. A 3 by 3 is plenty. And if you wanted, then from there, you could apply it to 4 by 4 or greater. So we're going to just say has 3 columns. The first column will be A1. The second column is A2. And the third column is A3. Now, here's what we're going to do. We're going to make up a matrix. We're going to call it capital X1. And capital X1 is going to be a square matrix where what we do is we put x, the vector x, in the first column. So what do we fill out the rest of the columns with? Well, we fill it out with just the columns of the identity. So the second column, we would use the second column of the identity. And the third column of the matrix x1 would be E3. Now, if you're not sure what that would look like, that's this, we'll write it in a second, because what I want to do now is I want to find out what that product is. So let's try that. So if I take A times x1, that's going to be, now we're going to write this out. This is A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so there's the matrix A, just the general matrix, times, now what would the matrix of X look like? Well, the first column is the vector X, and we've seen that many times before. That's X has components X1, X2, X3. And then the second column of the 3 by 3 identity, E2, is 0, 1, 0. And the third column of the identity, 0, 0, 1. All right, well, let's multiply those two together and see what we get. So notice this. When I take A11, A12, A13 times X1, X2, X3, that's going to be a dot product. That dot product, well, if I didn't have, let me do this. If I didn't have all these columns in here, then I know the answer would be, it would just be B. So my point of all that is we get row 1 of A times column 1 of X1 gives us B1. And row 2 of A times column 1 of X1 is B2. And row 3 of A times column 1 of X1 is B3. Now the next pieces aren't too hard. The second column of X1 says we want a linear combination that only includes the second column of A. So that gives me A1, 2, A1, 3, oops, Nope. You should have said something. Oh my gosh. A2, 2, A3, 2. And then the third column of x1 says we want a linear combination of A that takes none from the first column, none of the second column, and exactly one of the third column. So that's A3, 1, A3, 2, A3, 3. That is the matrix. We're going to call this capital, because we're going to use capitals for matrices. So we're going to call it capital B1. Just like there's an x1, there's a b1, and you're going to see there's going to be an x2 and an x3, likewise a b2 and a b3 that correspond. Well, now look at what we have. We have 3 square matrices. So Cramer's rule, I think we have just let's come up here. We need enough room. So Cramer's rule, well, let's just try this. A times x1, and I'm going to take the determinant of both sides, equal, and then let's take the determinant of the right side. Okay, on the left-hand side, well, this becomes the determinant of A times the determinant of x1 is equal to the determinant of b1. Now, the determinant of A, we have the cofactor formula for that, and for the determinant of b1, well, we could apply the cofactor matrix to that, and both of those look complicated from the matrices down below. So then my only hope for something that might help us out in a more obvious manner is to consider the determinant of the matrix x1. So let's come over here and let's try that. If I take the determinant of x1, then that is, you know what, just looking at that doesn't look helpful. But I know that if I can take the determinant of x1, that's also the same as the determinant of the transpose. Let's try that. That's going to give me x1, x2, x3 in the first. So the first column becomes the first row. Then the second column becomes the second row, 0, 1, 0. The third column becomes the third row, 0, 0, 1. Oh, and look at that. The determinant of a diagonal matrix, that is very simply the product of the diagonal. So that just says that the determinant of x1 is the first component of the vector x. Wow, there it is. So let's see this. If I solve this equation, I'm going to use this fact over here, then I can write this as the determinant of A times the first component of the vector x is equal to the determinant of b1. In other words, x1. And remember, you can divide because the determinant is just a number. It may be a difficult number to get, but it's just a number. So that's just the determinant of b1 divided by the determinant of A. Whoa, pretty slick. Well, it gets even better. So let's just check. Here's how the process continues. So now we have the first component. To get the second component, what we would do is we use A times the determinant of A times the determinant of the matrix x2 is equal to, you'd go through that same process, the determinant of b2. Well, here's how x2 and b2 have changed. B2 is going to be the matrix now where we have, you know what, let me do it this way. I was trying to be conservative with my space, but you know what, let's just grab another page. So let's do this. All right, so now let's solve for x2. So the matrix, so now we're going to use the same application, A times the matrix x2 equals b2. Well, A is the exact same matrix as we've had before, so I'm just going to leave it as A1, A2, A3. But x2, now we put x in the second column. So that means the first column is E1, or the first column of the identity. And then the x vector now is in the second position, x1, x2, x3. And then we put E3 in the third column. And so when we multiply these together, our result is we get the first column of A in the first column of B2. We get the matrix of A times the vector x. Well, that's the vector B, which has components B1, B2, B3. And finally, our third column becomes the third column of the matrix A. Sorry, that was an ugly looking A. It's terrible. Okay, A3. So now my one question is, what is the determinant? What is the determinant of x2? Oh my gosh, look at this. I had to think about that. Look at this. 1, x1, 0, 0, x2, 0, 0, x3, 1. Now, here's what's so amazing about the determinant is it's unaffected by row operations. So I could work on row 3 by subtracting x3 divided by x2 times row 2. And what I'm going to get is I'm going to get a diagonal matrix. The determinant of a diagonal matrix is then just the product of the diagonal components. And in other words, we're going to be left with 1 times x2 times 1, which is simply x2, the second component of x. And so repeating the process now, we have the determinant of A times x2 is equal to the determinant of B2. So you can say that x2 is equal to the determinant of B2 divided by the determinant of A. There it is. And just to show you that the last setup is going to be A, x3, B3, where A is the same matrix. It's A1, A2, A3. X3 now means we put the vector x in the third column. So I'm going to just write it. I think we're getting better at this. We have E1, E2, and then we're going to have x now in the third column. Well, if you multiply those together, that gives you the matrix B3. Well, that's going to have the first column of A in the first position of B3, the second column of A in the second column of B3. And then if you take the linear combination of the matrix A times the vector x, well, then you get the vector B, which has components B1, B2, B3. And now when you take the determinant of both sides, the key is, look at this. The determinant for the matrix x3 is the determinant of, this is going to be a 1, 0, 0, 0, 1, 0, x1, x2, x3, and there it is. You can see that this determinant is just the product of the diagonal components, which is just 1 times x3, which is x3. And there it is. And you divide both sides by the determinant of A, and you can say that x3 is equal to B3, the determinant of B3, divided by the determinant of A. And so your final answer is that the vector x can be written, which remember has components x1, x2, x3, is equal to, it's equal to the determinant of B1 divided by the determinant of A. x2 is the determinant of B2 divided by the determinant of A also. And x3 is B3, the determinant of, whoops, it's the determinant of B3 divided by the determinant of A. And that is the solution to your system of equations using Cramer's rule. We're going to try that a specific example in the next video. I hope that helps, and thanks for watching.